So, what are we working on tonight? Okay. Sirens going off all over the place where I live here. That's unusual to hear that many.
So today we have inverse sine and inverse cosine.
Okay. Let's talk about that for just a moment. If the sine of 30 degrees equals 1/2, which it does, by definition, the inverse sine of 1/2 equals 30 degrees. Okay? These two are if and only if. Both of those mean the same thing. What's important to understand is that if we take the trig function of an angle, we get a number or a ratio. Well, if you take the inverse trig function of that number, you get the angle. That's the definition of inverse. Is when you're taking inverse trig functions, you're always trying to find an angle. You're not trying to find a number, you're trying to find an angle. Whereas when you take trig functions of an angle, you get a number. So that's the most important thing to understand, is that these two things mean the same thing. Okay, so what specific problems do you have?
One is inverse tangent 0, and this is to find the exact value. I'm guessing that one's probably just going to be 0 then, right?
Well, it doesn't have to be, but if I graph tangent, turns out that tangent of 0 is equal to 0. So the inverse tangent of 0 is also equal to 0. But if it was cotangent, it would not be that way. In other words, it just happens to be that. I'm sorry they gave you that problem because it doesn't illustrate much. What do you got next?
There's more there. So next one is the inverse tangent of 1.
All right, that's a little better. Remember, it's the inverse tangent of a number, so we're going to get an angle question is which angle is it where tangents equal to 1? In other words, what is that angle on the x-axis?
That'd be 90 degrees.
Now let's look at our 45-45 triangle.
Oh, okay.
Remember, tangent is opposite over adjacent, and the dimensions on this 45-45 are that. So which angle is the tangent equal to 1?
45.
That's 45 degrees if I'm labeling in degrees. If I'm labeling in radians, it's pi over 4.
he probably wants us to be doing it in radians. So.
Okay, we'll label everything in radians. However, that's fine, except when you figure out all of your first quadrant angles, these two triangles are labeled in degrees. Now, of course, you can convert them to radians, but it's important to memorize these two triangles, whether you're in radians or not. If you're in radians, then this is pi over 4, this is pi over 6, and this is pi over 3. But the most important thing you can remember is the dimensions on those two triangles, because that pretty much answers all of your trig functions for any angle in the first quadrant that's a multiple of 30, 45, or 60 you get from memorizing these two triangles. Or you get from memorizing. I mean, you don't have to memorize these two triangles, but these two triangles you've been dealing with for 3 years now, right? I'm sure you got introduced to these at least 3 years ago. So you have a lot of familiarity with these triangles, so I'm inclined to memorize these triangles in terms of degrees and translate accordingly. But these two triangles is what tells you that the tangent of 45 degrees is 1 over 1. Therefore, the inverse tangent of 1 is 45 degrees, or pi over 4. Notice that that times that's always 180. Okay? Let's leave those two triangles up there. What do you got next?
Inverse sine of -1 over root 2.
Which angle is that from my two triangles? In other words, if I said to you the sine of which angle is equal to 1 over root 2, and let's ignore the negative sign for the moment. Let's treat these like we treat all trig functions. Let's figure out the angle first, and then figure out which quadrant it's in.
So 45 then?
Yeah. 45 degrees is our first quadrant angle. But clearly, the sine of 45 degrees is not -1 over root 2. Which quadrant do they want? Because notice that in your unit circle, all students take calculus. Sine is positive there, it's positive there, it's negative there, it's negative there. So which quadrant do they want?
Fourth quadrant?
Yes, always first or fourth for sine and tangent. If you're talking cosine, it's always first or second. In other words, if we want the principal value, we're going to give the fourth quadrant value. What angle is that? What's the fourth quadrant angle that's the equivalent of 45 degrees?
315.
That's your answer. Or 7 pi over 4.
Right.
Now, why did I not give the third quadrant as the answer? Because the sine of 225 is also -1 over root 2. And that's true. So it depends on the domain they gave you. If they gave you a domain of 0 to 2 pi, then we have to give both answers. We got to give 315 degrees plus we got to give 225 degrees. But if you put this problem into your calculator, it only gives you the principal value, which in our case is the fourth quadrant. It will not give you the third quadrant answer in your calculator. And we only know that the third quadrant is an answer if we know that we're looking for all answers between 0 and 2 pi. If they don't specify a domain, then the answer is 315. That's what your calculator gives you.
Okay.
For sine and tangent, any plus is first quadrant, any minus is fourth quadrant. For cosine, any plus is first quadrant, any minus is second quadrant. Those two things are what you need to memorize.
Okay.
Because when they ask you questions like this and they don't specify a domain, then they mean the principal value.
Okay.
And that's 315 degrees. What else?
Well, next one is the inverse sine of 1.
Okay. It's difficult to get that from those two triangles because these two triangles only deal with 30 degree, 60 degree, and 45 degree. Whereas if I graph the sine curve, there's only one place in the unit circle where that's equal to 1. Where is it?
Pi over 2.
Yeah. And that's the answer. And in this case, there's only one answer. That's it. Because that includes the whole unit circle there. That's 2 pi. And there's only one spot that it's equal to 1 right there. There's only one spot it's equal to minus 1. Any other value, and you're going to find 2 spots. In other words, if I said inverse sine of minus 1/2 or 1/2, well, it's equal to 1/2 here. It's also equal to 1/2 there. And any other number has 2 values. That's first quadrant, that's second quadrant. But when you're dealing with the quadrangles, which is this, quadrangles being multiples of 90, then you only have one value. Whether it's principal or not. In other words, that's the only answer for that, assuming you're within the unit circle. Now, you could also say that 5 pi over 2, in other words, the sine of 5 pi over 2 is also 1. And I can add 2 pi to this, so 9 pi over 2 is the same thing. In other words, all of these are correct answers. They're just not the principal answer, and they're not the answer that's inside the unit circle. But they're still answers. If I said, what's the sine of 5 pi over 2, the answer is 1. Are they defining the domain on any of these, or are they just leaving it blank?
They haven't defined the domain for any of
Okay.
those.
If they're not defining the domain, then you want to give the principal answer, which is the one you get from your calculator.
Okay.
A lot of times they'll say, okay, if theta is inside 0 to 2 pi, then they've defined the domain, and you'd want to find both quadrants that satisfy the inverse. Sometimes they might say theta is between 0 and 4 pi. So you'd have to go out 2 unit circles and find all of the angles where the inverse was true. But if they don't specify, they usually mean the principal value, the one your calculator would give you. Unless they want answers like this. Have you seen any kind of answer like this?
No, we haven't.
Okay, because notice what that means, and that means K is the subset of all integers. So if our answer was pi over 2, well, K is 0, it's still pi over 2, but when K is 1, we get 5 pi over 2. And when K is 2, we get 9 pi over 2. In other words, if they don't really specify a domain, then they kind of really mean all of those. And you can define all of these with this kind of an answer. And it's not always K, sometimes it's N, but it means the same thing. It means either N or K is a member of all integers. But if you haven't seen that kind of notation, then I expect that's not what they're looking for in these problems.
Yeah, you said that if I took calculus next year, and that's what I would be doing.
Yes. Once you get calculus, or sometimes in pre-calc, they'll have you give answers that way. In other words, they'll ask for all the answers, domain non-restricted.
Yeah, you told our class not to worry about it for now.
Okay, good. I'm glad I brought it up because I wasn't sure whether you needed to know that or not.
Yeah, I know what you're talking about now. I didn't recognize when we wrote it.
Okay. What else you got?
One just to do pretty much the same thing, but with a calculator, and it gives kind of odd numbers.
Okay.
So the first one here is inverse tangent of negative 12.5, and it wants answers in degrees.
Let me bring up my calculator here. I'm in degree mode. And you want the inverse tangent, so it's second tangent of minus 12.5. There's the minus 12.5. I don't actually need the last parentheses because it can be nothing but that. So that's minus 85 degrees. Now, this brings up a good point. When you're using your calculator, notice that I said when you're dealing with tangent, it's going to give you positive numbers in the first quadrant. It's going to give you negative answers in the fourth quadrant. Well, minus 85 degrees is fourth quadrant. If I go this way, there's my 85 degree angle. Now, that's the same thing as that, but it's measured as a negative angle. In other words, it goes clockwise instead of counterclockwise. So when you're using a calculator and you're dealing with negative numbers, you're going to get negative answers unless it's cosine. And then you would be getting second quadrant answers. But with sine and tangent, they're not going to give you the fourth quadrant answer. They're going to, which would be 275. In other words, that's 275 degrees. That's a legitimate answer. It's the same answer as minus 85 degrees. Okay? What else?
now I want to express the answer in radians, and it's inverse sine of negative 0.46.
Which quadrant are we going to be in once we get our answer? Remember, this is a number. Our answer is an angle. Which quadrant will it be in?
Will that be fourth
Yes.
quadrant?
Yes. So let's verify. Inverse sine of negative 0.46, negative 27 degrees, and they wanted that in radians, so I'll switch to radian mode. Hit enter, it'll give it to me in radians. Negative 27 degrees is minus 0.478 radians.
Okay, there's one here, I don't know what this means really. It says arc cosine.
Arc cosine's the same as inverse cosine.
Oh, okay.
Those words mean the same thing, inverse and arc. In other words, arc tangent's the same as inverse tangent, arc sine's the same as inverse sine, so forth.
Alright, thanks.
Of what angle? Or, excuse me, of what number?
This one is 0.17, and I want plus 1 in degrees.
Okay, let's change our mode back to degrees. What quadrant is this going to be in?
That'll be the second.
Are we getting an angle or a number? Is our answer going to be an angle or a number? Yes. Where is cosine positive?
In the
First and fourth.
yeah.
So the principal is first. If this was negative, what quadrant would we be finding our answer in?
Fourth.
No, cosine is positive in the fourth. So the principals for cosine are first and second. It's different than tangent and sine. Tangent and sine are first and fourth, but cosine is first and second. So if I have a negative answer, I'm going to have a second quadrant answer. If I have a positive, I'm going to get a first quadrant answer, and I'll show you. Okay, so we got the inverse cosine of 0.17. So that's 80 degrees. They wanted degrees, right?
Yeah.
Okay, now let's put in the inverse cosine of negative 0.17. What should that be? What's the equivalent angle to 80 degrees only in the second quadrant?
Not sure.
It's 100. Remember that when you're in the second quadrant, it's 180 minus theta. That's what your reference angle is. Okay, so if theta was 100, I'd end up with 80. So theta is 100. Let's make sure we come up with 100 when we do this. Second cosine of negative 0.17 100 degree, or supplementary to the first angle. A little round off error there, but notice it did not give me a negative angle. If you take the inverse sine or the inverse tangent, you always get the fourth quadrant angle, and they always give it to you as a negative angle. So that's something you have to pay kind of attention to, is that your calculator treats sine and tangent different than it treats cosine. Cosine, you're going to get either a first quadrant angle or a second quadrant angle. Tangent and sine, you're going to get a first quadrant angle or a negative angle, which will be fourth quadrant. What else, Daniel?
And next we have like kind of combining functions. So this one is sine of inverse tangent 1.
Always work from the inside out.
Okay.
In other words, this is going to produce what? An angle or a number?
That'll be the angle.
Okay, then we'll be taking the sine of an angle. So let's figure out which angle that is. Are you supposed to be able to use your calculators here or not? Probably not.
Yeah, no calculator.
Let's minimize that. It's the inverse tangent of 1. What angle is that? First of all, what quadrant is it?
That'll be the first quadrant.
Okay. Go up here, look at those two triangles. Which angle is the tangent equal to 1?
45.
Okay. So this answer is 45 degrees. Now what's the sine of 45 degrees?
That'll end up being, that'll be like 1 over root 2, but I can't remember, is it root 2 over 2?
Yeah. How do you rationalize 1 over root 2?
So you would multiply the denominator by root 2. Well, you would multiply both of them by root 2, so root 2 over 2.
That's how that is equal to that. And on these kind of problems, just always work from the inside out and you'll never have any problems. And always use the principal value answer from the inside out. In other words, the tangent's actually also equal to 1 at 225 degrees. If you go into your calculator and you say, what's the tangent of 225 degrees, it's going to tell you 1. But notice the sine of 225 degrees would be minus root 2 over 2. So I don't get the same answer. And that's why it's important when you're doing these double things like this, that you always start from the inside out and you always answer this with the principal answer. In other words, if this thing's positive, we're going to be in the first quadrant. If this answer's negative, we're going to have a negative angle. Or fourth quadrant.
So the next one is the cosine of 2 versus sine 1/2.
Cosine of what? 2 inverse sine of 1/2?
Yeah.
Okay. Again, work from the inside out. What's the inverse sine of 1/2?
That would be
So now we have 2 times 30 degrees. In other words, working from the inside out. So now we're looking at the cosine of 60 degrees. What's the cosine of 60 degrees?
That would be root 3 over 2.
Remember, we're 60 degrees. Adjacent over hypotenuse?
1 over 2 then?
Uh-huh. So there's your answer. Right here. Now, something that's worth knowing, let me just go through this.
Okay.
These 3 functions are either odd or even. 2 of them are odd, 1 of them's even. The top 2 are odd, meaning that the sine of negative theta is equal to minus the sine of theta. Or tangent of negative theta is minus the tangent of theta. Cosine is even, meaning cosine of negative theta equals cosine of theta. In other words, these have the same properties that your polynomial functions had that were odd or even.
Okay.
Okay? And that's worthwhile because they frequently give you your inverse sines and tangents as negative angles instead of as positive angles. So at some point you're going to have to deal with these properties. The fact that the sine of minus 30 degrees is the same as minus the sine of 30 degrees. Well, the sine of 30 degrees is 1/2. So the sine of minus 30 degrees is minus 1/2. Okay. Go ahead and give me your problems, and I'll bet it comes up.
Okay. So this is the inverse cosine of tangent pi over 4.
Now, let me go back and clarify something. I said we take trig functions of angles to get numbers. We take inverse trig functions of numbers to get angles. Well, that's only when we're talking degrees. Okay? Radians are actually numbers. They're not angles. So when you start dealing with radians, that statement that I make doesn't make any sense anymore. But I make it because I think it's important to understand the relationship between trig functions and inverse trig functions. And when you're dealing in degrees, you're always taking trig functions of angles to get numbers, and you're always taking inverse trig functions of numbers to get angles. If those angles are in radians, then it doesn't matter, it's still an angle. Okay? So, what's the tangent of pi over 4? What's the inverse cosine of 1? There's the cosine curve. Which angle? There's your horizontal axis is your angles. That's y equal cosine of theta. Which theta gives you a value of 1? There's only one on there.
0.
Uh-huh. So the inverse cosine of 1 is 0 degrees, or 0 radians. But it's a number. I mean, it's an angle, excuse me. In other words, this produced an angle, that produced a number, and then we took the inverse cosine of a number to get an angle. It's useful to always think of it in those terms, whether you're dealing with degrees or radians.
So now it says to use transformation to describe how the graph of a function is related to a basic inverse trigonometric graph. State the domain and range.
Okay.
The first one is the inverse sine of 2x.
All right. Let's talk about inverse trig functions. In fact, let's talk about all inverse functions. That function right there is y equal x squared, right?
Yeah.
If I were to get an inverse function of that, it would actually look like this. And that's not a function. Does not pass the vertical line test. So in order to talk about inverse functions of this function, we restrict it to only x's greater than 0, or greater than or equal to 0. Now I can talk about an inverse function, because now the inverse function looks like that. And this does pass the vertical line test, so it's a function. Okay, now let's talk about trig functions. Well, if I have my sine function, and I were to take the inverse of that, I can tell that this is not one-to-one, right? Does not pass the horizontal line test. So if it's not passing the horizontal line test and I take the inverse of it, it's not going to be a function. It won't pass the vertical line test after I get the inverse of it. So what mathematicians do is they restrict this domain so that we can talk about the inverse function. And they restrict it to minus pi over 2 to pi over 2. In other words, those 2 points, between those 2 points, that's what they're going to restrict the domain. And notice what we're looking at here, the first quadrant and the fourth quadrant. That's why our principal values for inverse sine end up in either the first quadrant or the fourth quadrant, because they've restricted the domain. Now, if I restrict this domain to there, now when I draw the inverse of that, notice that this is one-to-one. In other words, this is the original function, sine of x, but only graphed between minus pi over 2 and pi over 2. But it passes the vertical and the horizontal line test, which means when I take the inverse of it, it's still going to be a function. Well, to take the inverse of any function, you reflect it over the line y equal x. Well, what does this look like reflected? It looks like that, and looks like that. Something like that. Okay? So if I erase that, that's an imaginary line, and I erase the original function, there's my inverse function. That function is y equal inverse of x. You with me?
Yeah.
So inverse of 2x, what kind of transformation is that? Is that a vertical stretch, squeeze? Is it a horizontal stretch, squeeze? What is it?
Horizontal stretch.
It's a horizontal squeeze. When you have the number in front and it's greater than 1, it's a vertical stretch. If it's between 0 and 1, it's a vertical shrink. But when the number is in front of the variable like this, if it's greater than 1, it's the opposite. It's a shrink. If it's between 0 and 1, it's a stretch. So this is a shrink by a factor of 2, meaning instead of going from minus pi over 2 to plus pi over 2, I'm going to go from minus pi over 4 to plus pi over 4 with that same function, only it's now squeezed, horizontal squeeze. So I erase that one, and I've got that one now. And that's how we graph that inverse trig function.
Would that be the domain right there?
The domain is minus pi over 4 to plus pi over 4.
And how do we find the range?
Well, let's plug those in. When this is minus pi over 4, then I'm taking the inverse sine of minus pi over 2. What's that? Here's the sine curve up here.
So that'll be -1.
Correct. There's pi over 2. There's minus pi over 2. So the inverse sine of minus pi over 2 is -1. And going to the right side of the domain, pi over 4 times 2, well, that's the inverse sine of pi over 2. That's clearly +1. So the range still goes from -1 to +1, which you would expect, right? In other words, inverse functions switch the domain and range. If I draw a sine curve like this, what's the domain?
Negative infinite to infinite.
What's the range?
-1 to 1.
Right. So if I'm talking the inverse of this thing, the only way you can talk the inverse is if you've restricted the domain. It merely switches the range and domain. In other words, the domain of the inverse function would be -1 to 1, and the range of the inverse function would be -infinity to infinity except they have restricted it to minus pi over 2 to plus pi over 2, so that they can still call it a function. I think I answered the question. What was the original problem? Find the domain and range of that?
It said to describe the transformations of the graph as well. We did
Okay.
that.
Well, yeah, we did that. It's the inverse sine graph squeezed by a factor of 2. But it is important to know that if I said, what is the domain of this, right here in the lower right, what is the domain of that?
I'm not sure.
It's minus pi over 2 to plus pi over 2.
Oh, right.
Because if I make it any wider than that, then I don't have a function. I'd have something that looks like this. Wouldn't pass the vertical line test. So the only way the inverse is a function is if I restrict the domain from minus pi over 2 to plus pi over 2. In other words, this point here to this point there. Just that region right there. I can reflect that and I still have a function, and that is the inverse sine function once I reflect that. Now, tangent is similar. Notice, but there's something special about the tangent. There's the tangent curve. Well, that's 1 to 1. And that goes from minus pi over 2 to plus pi over 2. Also, notice, fourth quadrant, first quadrant, which we know inverse tangent is either first quadrant or fourth quadrant. I don't have to restrict the domain of this tangent curve in order to come up with the inverse tangent curve. The inverse tangent curve is still a function, and I can even go from minus pi over 2 to pi over 2. It's only the sine and the cosine that needs to be restricted. Now, if we look at cosine, the original cosine curve, notice that if I reflect that over the line y equal x, I would not have a function. That is not, in other words, the inverse of this does not pass the horizontal line test. So the way they restrict the cosine curve is between 0 and pi, first and second quadrants. So between that point there and that point there, if I reflect that, that's 1 to 1. From there to there, in other words, between 0 and pi, the cosine curve is 1 to 1. So I can talk about the inverse cosine curve. That's why my principal values for inverse cosine of positive numbers is first quadrant, and for negative numbers, it's second quadrant. So what's the specific problem?
So fx equals 3 inverse cosine x over 2.
And we need to say what kind of translations are we dealing with here?
Yeah.
Well, hold on. Let's first of all draw the cosine curve. that much of it. That's pi. That's 0. That's our domain restriction. For the cosine function, in order to come up with the inverse cosine function. So what does the inverse cosine function look like? Well, let's reflect this over that line. And let's see, this is always tough for me to do. For some reason, I have a hard time reflecting these things. What does that look like? Let's see. See, this point goes to if I reflect that curve about that line, then this point, let me do it in blue so I can see what I'm doing here. Well, this point goes to why am I having a hard time with this? Inverse cosine. It's got to go from 1 to 1. And it goes from 0 to pi on the y-axis. Let's see, this point right here reflects the right there. And this point is the same. And these points down here reflect to way up there. I don't know why I'm having a mental block here. But we need to reflect the cosine curve between 0 and pi about this line to come up with the inverse cosine curve. Okay? Now, once we get the inverse cosine curve, what's happening to it? What's the consequences of the 3?
That'll give it a stretch.
Correct. What's the consequences of this 1/2 coefficient in there?
So that'll give it a horizontal shrink.
Stretch.
Stretch.
Remember, if these numbers are greater than 1, it's a stretch. If these numbers are greater than 1, it's a shrink. And vice versa. If this number in front is less than 1, it's a shrink. And if this number in front is less than 1, it's a stretch. So we have a vertical stretch by a factor of 3. And we have a horizontal stretch by a factor of 2. And whether I can draw it or not, that's really, I don't need to be able to draw it, right? Is all they're asking for is what translation is happening. So the answer to the translations, you don't even need to know what the graph looks like. You really, what's that?
It also needs the domain and range.
Okay. Let's talk about this. What's the domain of this?
That would be negative, or would that just be 0 to 1?
Negative 1 to 1.
No.
What's the range of it? Remember, domain and range merely switch. In other words, if I know my domain and range for cosine x, then I know my domain and range for the inverse, except for the fact that I've had to restrict it. So the range doesn't go from negative infinity to infinity, it goes from 0 to pi. Okay, you with me there?
Yeah.
Okay, so if the domain and range of that function is what I've written in blue, then the range of this function is from -3 to 3. Hold on. Excuse me, I got it reversed. The range of the inverse function is 0 to 3 pi, 3 times this range of this function, and the domain is still -1 to 1.
Well, what about the horizontal stretch by 2? Would that affect it?
That only affects the horizontal, and that, oh man. I've confused myself now. Let me think for a moment. Okay, if I'm talking this function here, the domain is -1 to 1, and the range would normally be all real numbers, but since we've had to restrict the domain to even talk about the inverse function, then the domain of this function is 0 to pi.
Okay.
Hold on. Let me go back. Let's see. If f of x equals cosine of x, the domain is 0 to pi, the range is -1 to 1. So domain and range switch when you're talking the inverse function. So if I'm talking the domain of this function here, I'm talking -1 to 1. And if I'm talking the range, I'm talking 0 to pi. So these apply to this function right here. Okay? Well, how does the function in red differ than this function? Well, my range is 3 times, so it's 0 to 3 pi instead of 0 to pi. In other words, it's a vertical stretch. That's the range. My domain must go from -2 to 2. In other words, the domain is your horizontal, and I'm expanding it by a factor of 2. So I'm going to go from -2 to 2 instead of -1 to 1. So there's your domain, and there's your range for this function here. I'm 90% sure. Unfortunately, I'm not sure I have a way of giving you the 100% sure answer. I don't have a calculator won't tell us that. My Wolfram Alpha won't tell us that. But I'm pretty sure I've done the analysis correct. So I'm 95% sure that that's the right answer. The domain goes from -2 to 2, and the range goes from 0 to 3 pi. I might have to do a little research in my Trig book to verify that, which I can do before I talk to you. Okay? All right. Any last questions you want answered?
No, that was a good enough to cover it.
Okay. Daniel, I will talk to you next time. Next Tuesday, I guess. All right. Bye-bye.